Let me introduce myself. My name is Keith Church. I work with the Mount Baldy Ski Patrol. I am the Avalanche supervisor for National Ski Patrol for the Far West Division. So I supervise Avalanche education programs in California, Arizona, and Nevada. I'm a California licensed snow blaster, and I was doing some of that work last week. So tonight we're going to talk about snow science, and this is not going to be get out your pit card and your shovel. We're going to talk about snow. If I can get this to advance. Here we go. So what is snow? So snow are individual ice crystals. They're formed in the atmosphere. They accumulate on the ground. We're really, as ski patrollers, as practitioners, we are really only worried about snow on the ground. And let me tell you that although this is titled Snow Science, I am no scientist. I am a practitioner. That is to say, I've got degrees in political science and law. I took physics for poets in college because I wanted to avoid the calculus. So I don't work in a cold lab. I don't study snow in a clinical or a laboratory environment. Rather, I study it once it hits the ground. That isn't to say that we aren't interested in what's happening in the air. Once it hits the ground, that structure is what we would call a matrix. It's got an ice grain skeleton, but the snowpack itself is made of air, ice, and liquid water. The type of crystal is dependent upon how it was formed in the atmosphere, and so that part is interesting to me. And I can tell you that when I was driving up early Friday morning to Mount Baldy to do some control work, I saw a couple of flashes of lightning. That lightning told me that I was going to see some graupel. I was going to see some thunder snow, some snow crystals that had been rimed as that storm, the cyclonic lifting, carried grains up, and then they fell back through the air column, hitting supercooled air, getting all lumpy looking, like styrofoam, being lifted again multiple times until they finally dropped to the snow. And so we did see graupel mixed in about 2 hours later while I was out. Snow is always going to be six-sided. So any crystal is going to be six-sided or starts its life six-sided when it's formed in the atmosphere. And that is because of the shape of the water molecule. So you've got if you imagine the oxygen molecule is my head, the hydrogen will attach at about 104.5 degrees naturally. Its two electrons are going to attach right here. So my hydrogen is here when as those other electrons, the other 6 electrons are spinning around my head, the oxygen, it's actually going to pull these down to about almost 107 degrees. And then when I touch another water molecule, that is oxygen with hydrogen attached, it's going to pull it down to 108 degrees. So I go from kind of teddy bear to Mickey Mouse when we form. And as a result, we have 120 degree angles, outside angles on all of our snow crystals. So this slide has been stretched so it doesn't look like a perfect hexagon. But hexagon shapes are generally what we will start with. The most common form of snowflake is a plate. And you will see that they form at 0 degrees C to -3 C. And then they start forming again at -8 to -25. And that's because different forms of ice, crystals, will develop based on not just temperature, but also humidity or supercooled moisture adjacent in the atmosphere, and the pressure, essentially a pressure differential between the cold and the hot. And as that pressure goes up in the middle of the curve, we get some columns, or rather plates, growing on the front end of that curve and on the back end of that curve. So at the top of that curve is where we're going to see growth of things like stellars, the dendrites, those really pretty six-sided, what you would see around Christmas time on a Christmas card. Same thing with columns, which are just a stacked plate, essentially, whether hollow or solid. They will form at the very coldest and at the near warmest temperatures. Once snow hits the ground, we start looking at settlement. So this is, we're going to talk briefly about the dynamics, the mechanism of settlement. We'll talk about settlement rates, and we'll talk about how that affects snow stability from an avalanche perspective. So settlement itself is a function of gravity. It's a mechanical process, essentially, where snow falls rather loosely. Those crystals individually have broken up some, but they still hold some of their original form, or most of their original form. So they're bigger crystals. They're not going to pack down real tight, right? In the case of dendrites, their little their spikes may be hitting each other, and so there's quite a bit of airspace there. As we lose those angular, as we lose those the peaks. And we lose those outside angles as we start to see more rounding and things break off, whether by wind or just gravity. You will see these snow grains are starting to get a little closer together. And over time, as they get a more rounded shape, and we're going to talk about sintering or rounding later, the snow settles even more. So we get less air and less air in the matrix, and more crystal as a percentage of the matrix is as time goes along. So settlement rates, we really are looking for something around 15 to 25% settlement. Anything over about 12% is really good. You are typically, backcountry skiers don't have a storm boards. They don't have an hour board. They don't have a storm board. They don't have a 12-hour board. They don't have a 24-hour board. So you're not taking measurements, and you're not going to actually calculate exactly what your 24-hour settlement rates are. But there are some things that you can look at that will provide you some clues. These snow cones or snow teepees that we see at the bottom of these trees in the left hand of the slide are indicative of good settlement. That is, the snow is settling down relatively quickly. So we're looking for something around 15, 20%. Over 30%, we will.
I'm just waiting to hear back from Julie before I take off.
Oh, okay.
So yeah.
Let me mute some folks.
No problem.
Here. I'll ask Alan to.
Keith, as the host, you can unmute everyone in the meeting.
So, settlement rates of 30% or higher, you're going to see avalanche activity, natural avalanche activity. At those kinds of rates, you're probably not skiing anyway. But that is, if stuff is starting to come down around you, you're in the wrong spot. So again, settlement is a good thing, generally speaking. Snow falls in layers. And and each layer is made up of one or sometimes a couple of crystal forms that have fallen. Grapple falling with the columns that we got this weekend on Friday morning is not uncommon. But when that layer of snow falls, and you can have multiple layers out of the same storm. That is to say that you'll have a couple of different precipitation events that occur in the same storm. Each layer is going to have separate characteristics, density, type, temperature. Those characteristics are retained within the snowpack. They will change, and we are going to talk about metamorphism in a bit. They will change over time, but even in a completely isothermal snowpack, you can often see slight variations between layers that have fallen in the past. So there's some persistence in that difference. So we can see we are looking, when we are out looking at snowpack, we are looking at strength within within discrete layers themselves. And we're going to talk about that, what we would call cohesion. Then we're looking at strength between the, let me see if I can read it here. There we go. So we'll see, we're looking for strength within the layers, those discrete layers, but we will are also looking for strength between layers, that is the bonding between layers. So when we're talking about grain-to-grain bonding within a layer, we are talking about cohesion. So cohesive snow is snow that sticks together pretty quickly. Snow, it may have the actual slide that we are looking at here. We've got good necks built between these individual ice crystals. You can see lots of connection points between them versus non-cohesive snow, which is like sand. It's irrespective of its size, it doesn't stick together. And that has a lot to do with loose avalanches. Again, cohesion we see occurs between crystals in the same layer. Adhesion is between the crystals in separate layers. When it comes to adhesion, it's partly a function of friction. We're talking about that bonding. It is rarely as strong as the cohesiveness within layers. And that is because we're going to have slightly different, if not snow crystal types. We'll have snow crystals within each layer that are at a different point in their process of metamorphism. So the bonds between our layers can, it's just the very rare case where the bonds between the layers are stronger than the bonds within the layers, those discrete layers themselves. So the more snow we get on top, the more weight we put on the snowpack, the more friction we get, the more adhesion we will typically get. And a big piece of this friction has to do with like or similar or dissimilar crystal types. That's both size and shape. So the more that they are alike between two different layers stacked next to each other, the more they are alike in shape and in size, the better bonding we'll get between, the better adhesion we'll get between those two layers. So bonding within layers is really a function of the crystals interfacing with one another, how close they get together. It's affected by grain type and other forces. You can have very weak layers where facets, for instance, and we are going to talk about faceting, where you have very angular edges and there's not a lot of space for water vapor to form a neck between the individual grains, versus very rounded or sintered grains that have much more surface area to come into contact with one another, much more likely to bond together. So we measure the strength or the cohesiveness within a layer by its hardness. And the scale goes all the way from fist, whether I can push my fist through the snow after I've cut a wall, all the way to whether it takes a knife to actually get in there. And then fingers, pencils, things like that in between. We're measuring the hardness. So, and we want to remember that a harder layer within the snowpack can serve as a bed surface for an avalanche to run on top of. much the way ground can. So adhesion typically comes in, it's a factor in slab avalanches. So we have a slab, which is ranging from soft to hard, but is bonded snow within a layer that is forming that slab. If it loses adhesion to the layer of snow below it, it's going to slide off. It'll break up, but it will slide off as a layer. Cohesion within a layer is a factor in loose snow avalanches or sloughs. We do, while they can trigger they can trigger a collapse if they are buried underneath a hard layer, or just their weight running on the surface down onto a slope, we can actually trigger by adding weight suddenly to the snowpack below, we could trigger a slab avalanche below that layer of loose snow. But again, lack of cohesion in that layer is top layer is typically an issue when it comes to loose slides. So this is a photo of the slope right below Psych Out. So I was above that this weekend doing some control work on Friday and skied this area on Saturday. It was very good. Here we can see we've had some snow. It started in the trees and right at the interfaces of the rocks at the bottom of the cliff. Let's put out a little poll and you tell me what type of problem you think we've got here. So which avalanche problem or avalanche problem type is this? There are 9 types. I will tell you this is a west-facing slope. Happened, the actual slides, this picture was taken in the afternoon, but it was actually taken after a wind event coming from mainly the southwest. We had about 12 inches of snow, perhaps 10 inches of snow, about 24 hours beforehand. Now look at the shape also. You notice that it widens as it goes down. Okay, we've got 68% of you participating. Let's share the results. And the plurality of you got it correct. This was a dry, loose slide. If it was wet, it would have it would look slightly differently, but it's hard to tell from the pictures. If this were east facing, it would typically be a wet slide happening in the afternoon, but this happened in the morning. So what about this slide? This is across the street. I'm trying to remember the name of this peak. This is right across from Snowbird. I was up at the howitzer installation up there, the new one. This was 10 years ago. But before they got a chance to shoot it, this had occurred. This had occurred overnight. What kind of avalanche problem do you think this is? I will tell you that we had wind the day before. We had not gotten, this was later in the week, we had not gotten a whole bunch of snow. All right, and here everybody got it. That was a wind slab, about a 2-foot crown. on average across there. It was the result of a wind event. So when we look at these types, we've got wind slab. That occurs with existing snow on the ground that's being moved, suspended in the air, and is being transported to another spot. A storm slab is snow that is sliding as a result of fresh snow that has come during the storm itself. Loose dry is a good example of what we saw on Psych Out 2 slides ago, where we had loose snow that lacked cohesion, and it only took a few crystals to pop loose to start, and it will slide out in this sort of classic alluvial fan shape. It gets a little wider as it goes, and then it peters out eventually, or it triggers something bigger below it. Loose wet is something that we'll typically see on south, southeast, and eastern slopes, especially in Southern California, where we have, again, an unconsolidated layer, but it is running because it has lost the lack of integrity is because it has melted. We're going to talk about that type of instability in just a bit. Wet slab is where we have some good cohesion in a layer of snow, but it gets very wet due to melting or rain, due to warm temperatures or rain, and it will slide on some surface below, oftentimes lubricated, maybe a lubricated ice lens or a crust or a very hard and very cohesive layer of snow underneath, where the water doesn't perk down real well. You will get a wet slab. Persistent slab problems typically relate to a problem layer, oftentimes facets, sometimes buried surface hoar. It can be a snert layer, or just a layer where you have very, very different ice crystals by type or size that are a problem for a long time. We'll see some examples of that. Deep persistent slab is when you see deep persistent slab on the Avalanche Center website, you will these are slabs that are pretty hard to trigger as a person as an individual out there on skis, snowboard, snowshoes. But if they fail, it will oftentimes be very catastrophic. And they can be touchy and very persistent, last throughout a season. Cornice fall is an avalanche that's triggered by a falling cornice, a result of wind, as Alan explained last week. And if the cornice doesn't fall on you, or if the cornice doesn't break and you fall on top of the cornice can fall down onto the slope below and trigger an avalanche. We call these backcountry bombs. When we intentionally drop a cornice onto a slope, we are sometimes testing it that way. And then lastly, glide avalanches. And we're not going to get into creep and glide and total motion of snowpack because we just don't have that much time today. But these are you will see in spring, especially here in Southern California, you may see a near vertical walled crack in the snowpack running horizontally across the snowpack, where the snow has actually separated. It looks like a little moat. That's a glide crack, and if we typically in those cases we have lubrication at the ground surface, and if there aren't sufficient anchors, you'll get a glide avalanche. For those of you who've skied Mount Baldy, our run Huckamuck, which is southeast facing, is very prone to glide avalanches. I've seen it go all the way to ground a couple of times in the last 16 years. So back to our poll. This is the Baldy Bowl. This was March a few years ago. This was about 2 o'clock in the afternoon. Things have warmed up a bit. You will see the nature of the debris at the base, at the toe of these slides is kind of chunky. Tell me what kind of avalanche problem we're dealing with here. All right. At 67%, 87% of you got it right. That is wet loose. Came right out of the rocks near the top, near the summit. And remember that wet slides, particularly wet loose slides, can run a considerable distance even at low angle because they are sort of self-lubricating. Nevertheless, this is nothing to sniff at, as there's oftentimes rock or other debris in this stuff. It will grind you up, and it's moving relatively slow compared to other avalanches. But if you are in its path, you can see we had slides that came out of Gurley Man and out of the Hourglass chutes up here too. If you're in its path, you are and you are caught and entrained in this, you're going to take a real beating. You may have seen, I don't know, 4 or 5 years ago, I think Alan showed the video of somebody being airlifted out of this main. This slides frequently right down here in the middle of this Baldy Bowl. Well, you saw somebody helicoptered out with some substantial injuries. How about this? This was taken, I was in Utah. This is Inbounds at Snowbird. That's Bruce Tremper in the green jacket, and Jesse, I don't remember his last name, the fella doing push-ups in front of the snow, is the patrol director at Kirkwood, or was. I'm going to ask you what kind of slide you think this is. And let me give you a little information. We were in the middle of, I came at the tail end of an 11-day cycle, which was the biggest avalanche cycle they had had in 50 years. Everything that could slide slid. You can see 3 discrete layers in this wall of separate snow events during these series of storms. This top layer was actually wind transported snow. What Jesse's down on his belly looking at is what we call a snert layer. That is a layer of snow and dirt that blew up out of Salt Lake City. Dirt and sand, just grit and grime, that ended up on the snow, covered by several storms. And we saw multiple slides on multiple aspects of all sizes coming out on that same layer, that same snert layer. Okay. So we could say everybody vote. 63% of you voted for deep persistent slab. I would call this persistent slab. Deep persistent slab is something that would be really hard to trigger. And while we have about 20 inches of snow on that last layer, that was just snow that had been wind transported. I think that you would probably be on the bubble, but what the Utah Avalanche Center was warning folks of at the time was a persistent slab problem. It's not a storm slab because, as I said, that top layer, that third layer up, the one on the very top, is not actually from, it's from a previous storm, but it was transported by wind. And one of you said wind slab. Again, the wind depositing the snow is certainly what triggered this avalanche, this natural release. But the problem wasn't that top layer of wind transported snow. The problem was that bad interface on the snert layer on the bottom, on the 3 layers down. Good work. What about this one? I will tell you that this was, again, I was out with Tremper and some other folks, and we were east of Alta in this case. We had all agreed that we would clear out of there by 11 o'clock because we were worried about warming conditions. And we didn't. We snerted out. We found a nice safe spot to do a bunch of pits, and we started digging, and the day caught up with us. And on our way out, I took some pictures. So again, this is east facing, and this is by right around noon by the time we got, things had warmed up quite a bit. Okay, with 70% of you in, yes. 80% of you said it was wet loose. Again, hard to tell from the picture, but again, this is these series of avalanches, and as you look from the center to the left of this photo, you will see that we have multiple small slides, classic loose slide or loose avalanche shape, that alluvial fan, but in this case it was simply because it had warmed up. And again, we covered this guy, dry, loose snow. And this is just to the left of that, where that last photo was taken. This was taken not by me, by another patroller on near the top of Bentley's Dream, a run at Mount Baldy. Let me tell you that what we saw, what happened before this occurred. Somebody was out we had patrollers out ski cutting. We had snow. This was at the very tail end of a good storm cycle. We had dropped relatively light snow, but something in about the 15% density range. But we had about 20 inches of it. They came across. You can see he's ski cutting from skiers left to right. And if you look at the photo, you can see that little crack running back up the hill. And we had typically we had a number of slides like this with about an 18-inch face. And you all got it. That was a storm slab. You can see from the photo that they were still the tail end of the storm was still going on. It was still snowing. Good work. This is Friday morning. The time we finally got packed up, this was probably about 9:15 as we were arriving. We were past that last photo, Bentley's, in an area called Psych Out, above those cliffs that you saw in the photo a couple of times previously. And you can see that the cracks are running right off my skis, both skis. But your downhill ski has more weight on it, so that's the crack that runs a lot longer. But it's arresting. You can see it's actually to the right of the crack. You can see the spot where it has set down on this discrete slab of new storm snow, has sat down and arrested itself. I could not get it to move. Whether I skied fast, whether I jumped up and down, I couldn't get it to actually slide. But it was the shooting cracks were getting pretty long at some points. It felt a little touchy. So what we do in those cases, that is an airborne 2¼ pounds of high explosive with a 2-minute fuse on it to pothole those areas. We peppered the lower mountain pretty well to make sure we got some activity, but gives us a real good idea. When we put a lot of energy into the snowpack, we have a better idea of its likelihood of sliding on a skier or snowboarder triggered.
Hey, Keith, would you in that previous picture, would you say that there was no propagation within that release, and therefore it was arresting, and we wouldn't have seen propagation if we got into let's say an instability test?
Well, so to let you know that this did propagate. I mean, it cracked out and ran, but it arrested in place. We did manage to get Nightmare and Bentley's left side to slide, but that was sending Lars out with a snowcat and pushing half a ton of snow on top of it and getting it to release and slide out. So we had what I would call a medium soft storm slab that we were dealing with that day. The grapple that fell on it, luckily, fell on it and not under it. If the grapple had come before this about 12 inches of snow that we were dealing with in that layer, it would have been a much more exciting day for control work. So now let's get on to metamorphosis. I'm going to try and move quickly here. I apologize. We've been geeking out, but let's at least get through. I won't put up the poll about this is Franz Kafka, for those of you who get the joke, and it's not much of a joke. Metamorphosis, it refers to changing of shape when we're talking about ice crystals. So an atmospheric form may have started to change already, to the extent that in wind, especially if we've got cyclonic winds, it's getting broken up. Those pretty dendrites that we see in the left side of this picture get, a lot of the pretty little feathery ends get broken off just in the air as they're falling down. But once it hits the ground, we've got it will start to metamorphose by actually those ends where we have higher pressure are going to move water vapor will be pulled off the ends and into all of the open spaces around those crystals because there's more pressure. There's more air pressure around the ends, these blunt or pointy ends of each crystal. So generally, they're getting rounder in that case. So this rounding process happens typically between 0 degrees and minus 20 C. You have a vapor pressure differential between highly convex and highly concave structures. So convex structures are losing their water molecules, and they're being deposited into the concave structures. So those branches of those stellar crystals, those dendrites, those needles, they're starting to disintegrate, and the spaces between those branches are filling with water vapor and refreezing in that place. And then anywhere where the grains themselves are contacting, they will start to what we call neck. That is, in between those grains, we'll start depositing, again, low pressure zone right there. That's where we're going to end up depositing water vapor, and they will start to grow together. We'll get necks between them. So final shape, kind of irregular, not perfectly round. We call it rounding, but they don't get perfectly round. We have necks contacting in the second slide in the middle between the grains, and they are relatively strong. This is increasing cohesion in that layer of the snowpack. And in its most extreme form, you have a photo, something like the photo we have on the very bottom, fern ice, which is almost like glacial ice, where there's it's hard to differentiate the grains from one another. Faceting, what we used to call kinetic growth, happens at these same temperatures, although it slows the lower the temperature is. When we have a significant temperature gradient, those of you who were with us last week heard Alan talking about 1 degree C temperature differential within 10 centimeters vertically in the snowpack is indicative of a temperature gradient, is indicative of a pressure difference between those spaces. That means that we are moving vapor, water vapor within the snowpack itself, typically from the ground, which is always 0 degrees C, and upper portions of the snowpack that have fallen colder and have also may have cold ambient temperatures in the evenings. So, 5 millibars per meter is the significant pressure differential. We can't measure that. Theoretically, I guess you could develop something to do it, but it certainly wouldn't be a practical piece of equipment to carry out there. So the way that we measure that pressure differential, again, is in the temperature gradient. It's not the temperature. The temperature is indicative of the pressure difference versus the pressure difference being related to or driven by the temperature difference. I don't know if that makes any sense to you at all, but let me tell you, it's about pressure. But we determine the difference in pressure by looking at the temperatures. So final steps, we're going to get back to that original six-sided, or we're not necessarily six-sided, but certainly we're going to get back to what a six-sided crystal naturally forms. When water freezes, you're going to have 120-degree outside corners, 60-degree inside corners. And as it starts to go the other direction, facets will actually chain. So again, they're so angular, they have to find a spot where they can actually meet up and have enough surface area contact that we can redeposit vapor and start to round or sinter, go back the other direction and get stronger. So these facets are not strong. Skip that. Where we will typically find them, depth hoar, so deep facets, oftentimes very large facets, again, driven by temperature differentials, difference between the Earth's temperature, 0 C at the ground, and colder temperatures within the snowpack. We'll see surface hoar, we'll talk about that briefly, that forms on the surface, fasting above and below crusts, and then around rock and vegetation interfaces. So any of you who've taken our level 1 class this fall and are going with us to Lee Canyon the first weekend in March, that place is notorious, even in spring, for pocket hoar that forms around in depressions and around vegetation there, right on the surface. So depth hoar, again, found near the ground, found at layer interfaces also, because we may have a big pressure differential when you've got a crust or an ice lens, something that is stopping the migration of that moisture from warm to cold. It forms similar to the way that rounding occurs, but it's going the opposite direction. That is to say, instead of moving the grains from, or water molecules from angular surfaces into concavities, we've got this pressure differential, which is pushing water vapor from areas of high, warm parts of the snowpack to low pressure, colder parts of the snowpack. As a result, we're losing the tops of the crystals and we're building onto the bottom of the next crystal up. So if this is a crystal, we're harvesting or cannibalizing some of the water molecules off the top of this. It floats up or is pushed up to the next crystal where it hits the bottom, and it forms these very angular, again, 120-degree angled, outside angled shapes that may look like cups. Near surface faceting. We will talk just about surface hoar, I think. It occurs when we have calm, clear conditions. It occurs when we've got moisture, humidity right at the snow, at the layer of the snow surface, and we're losing heat right at the surface as long wave energy at night or in the shade is released through the snowpack from the earth, and when it releases from the actual snow surface, we get a supercooling going on there. Essentially, it's like dew running the opposite direction, and we will see these very feathery little crystals. This happens optimally when we have no wind, or maybe perfect conditions are about 3 miles an hour of wind, just a light breeze that's moving this moisture air and allow moving humid air into the position, constantly adding extra moisture right to the surface that allows us to build those crystals from the ground up. A very persistent form if it is buried, very difficult to find if it is buried. If it's buried on top of ice or a hard layer, it can be absolutely deadly, but it can be it's a persistent form. It can wreak havoc with the snowpack for a whole season. In some cases, if it is buried while it's still standing upright. Now, if you've got 10 miles an hour of wind or 15 miles an hour wind, that will typically blow those crystals over, and the surface core won't be a problem at that point. Mid-pack faceting above, but more typically below crust layers, where it's serving as a sort of a vapor barrier. So we may have a wind crust, we may have an ice crust or rain crust that is formed. We've got moisture trying to migrate from this warmer snow near the ground upwards into colder snow. It hits this crust as a barrier, and we're going to facet starting right below there. You may see, by putting in some thermometers, a very significant temperature difference between the bottom side of the crust and the top side of the crust. Also, as I mentioned, near vegetation and exposed rocks, we'll see some. Crusts, another persistent form, found can be caused by wind, can be caused by sun, which is melting, and can be caused by rain. Melt-freeze process. So this is also metamorphism, but is a different form because it relies on ambient temperature and really the sun to do its work. This is the diurnal shifts between day and night. We have a freeze thaw that produces larger and larger grains. So those of you who ski in Southern California and the Sierras in the spring, you love that corn snow, right? Right around 10:30, 11 o'clock as it starts to soften. When you make a big turn in it, you get these big grains of snow that come up. And that is because during the day, we're melting those larger, all of the crystals melt. Only the biggest crystals survive. They're able to self-insulate, and so the smaller crystals around them melt out entirely and become free water in the snowpack. At night, when we get a refreeze, they refreeze to those larger crystals. So with a proper freeze-thaw cycle, diurnal cycle, day and night, we're going to end up with larger and larger crystals, and generally really good skiing. Those crystals refreeze, and you'll see necks form at night. They'll freeze to each other. You don't want to ski it at 6 in the morning because hard as anything, no fun to turn. You wait for it to soften up just enough. When it turns to soup is when you got to run. So pendular regime, where we're getting a good swing from cold to warm day and night. We've got continuous air throughout the snowpack. We're getting some percolation where the water is actually running through the snowpack, not in big perk channels, but we've got water that's draining through the snowpack. And then we've got some surface tension with the distributed air, create some capillary action, which kind of holds those crystals together. When we get to a funicular regime, this is where things are problematic. We don't have good air distribution. You may see large percolation channels. If you were to dig a snow pit, pour some dye in the top, you may see spots where it's coming down almost like a drain pipe. Or we have layers within, maybe an ice lens or a crust below the surface, the immediate surface of the snow, that is stopping the percolation from happening. In those cases, it's not a good day to ski. It may not have frozen overnight either, in which case you're going to see, as you see in these photos, big roller balls. You may start to see some pinwheeling, and that is indicative of a slide, whether typically loose, wet, like we saw on Saturday at Baldy. We had east-facing slopes. I was watching it pinwheel in the morning. These end over end, a small piece of snow pops loose, rolls end over end, and gets bigger and bigger. We saw the picture. Somebody called them roses last week during, which I liked, during Alan's presentation. It was indicative of wet slides on the way, and within an hour and a half of the first of the pinwheels, we had 3 good size slides. Luckily, not too close to our actual runs, but stuff that people had skied, slid, wet. When you're determining total water content, the typical way to do it is actually grab a handful of snow and squeeze it with a gloved hand. and that tells you how much water you're pulling out. Tells you whether you are dry, moist, wet, very wet, or slush. If you squeeze it and it just squirts out, that's slush. That's a good time to pack your stuff up and get out of there. Head to the bowling alley. But wet, in spring where we're skiing, we'll pick up and we'll squeeze real hard, but we'll get just a little bit of a drop or two of water out of that snow, and it makes that really good snowball that you could knock somebody out with. That's okay. Wet snow is okay, but very wet snow or slush is a problem. I'm not going to get into calculating. I will tell you that snow water equivalent is different than moisture in snow, the way that we calculate moisture in snow. And snow density we will save for another time also. That's a lot. But let's get to the isothermal snowpack. And it's something that we'll typically see in spring. That is when all layers of the snowpack are the same temperature. We sometimes call it an equitemperature snowpack. It is, in Southern California, often preceded by a good-sized rain, which will run all the way through the snowpack or most of the way through the snowpack and sort of equalize the temperatures. And this is really typical of spring. Sometimes we'll see this mid-January when we get that classic 2-week thaw in Southern California also. But in those cases, the snow is all pretty close to 0°C from the ground to the snow surface. Generally pretty safe, although again, we have to worry about the freeze-thaw cycle and whether the top of this stuff is freezing sufficiently, or at least not melting so much during the day that it becomes a problem. So before I ask questions, let me give you some suggestions for additional resources. SnowSense. Get the 5th edition, most recent one. Simple, quick read. It is something that we've used for all of the editions in the past. We've used for years as a level 1 Avalanche textbook. More recently, we have moved to, we have switched off from time to time with Tremper's Avalanche Essentials. Also, a relatively short read, very accessible, a great entry to the field and the avalanche danger. If you can find it, La Chapelle's ABCs of Avalanche Safety, a good one. 3rd edition is out. This is a 2nd edition. Daffern, Tony Daffern's Avalanche Safety for Skiers and Climbers, another good one. It is now in a 5th edition, I think. Tony gave me a copy, but it was on a CD, so even the 5th edition is quite old at this point. Staying Alive in Avalanche Terrain. There's now a 3rd edition. This is a 2nd edition. Top-notch book. This is for folks who have maybe taken a level 1 and are thinking about moving on to a level 2. A wealth of information without getting way over the tip top with jargon and science. And then Avalanche Handbook is what has historically been called the Bible for the 3rd edition now. That's the 2nd. The 3rd edition, everything about avalanches you could possibly want. Lastly, what ski patrollers call the Bible, and mandatory for a level 2 class with NSP, is the swag manual. So that's Snow, Weather, and Avalanche Guide, produced by A3 and the National Forest Service. And then, of course, the International Classification of Seasonal Snow on the Ground is another highly scientific reference book. And the Avalanche Handbook really is a reference book also. I mean, it's not the kind of thing that I've ever sat down, just read cover to cover. It's usually something that I hit the index to look up a particular issue or to find a term.